Hello everyone, welcome to this online NPTEL course. And today we are going to have the tutorial class for the transmission electron microscopy section. In this class we will solve some problems like we did for an X-ray diffraction. One thing you have to remember that when you talk about the diffraction concept, it is one and the same whether it is for X-ray or an electron. So all the diffraction concepts we explained through Bragg's law, and then we solved several problems involving Bragg's law, and we also talked about some lens aberrations and then the kind of resolution limit and so on. These expressions will be same in the case of electron microscopy also, which you have seen in the lectures as well. So we will try to solve some problem which is very specific to transmission electron microscopy, and then we will also try to solve some of the single crystal electron diffraction pattern and how to do it manually, though these days mostly computers are used and software packages are used, but you should know the calculation behind this the software results. And also in later part of this tutorial, maybe after a couple of tutorials classes, I would like to give you a lot of conceptual questions, and then probably we will answer most of them, and then I will also post online a lot of conceptual or self-assessment questions, and also some of the questions will be based on the lecture notes, so that you can have a plenty of opportunity to assess yourself how much you have understood this course, and which will be useful for you in solving the assignment problems as well as at the end in the exams also. So now let us look at some of the typical problems which I would like to give for this tutorial. So the question reads like this: an electron probe of 10 nanometer diameter is formed in a 100 kV STEM, scanning transmission electron microscope. The convergent semi-angle alpha of the probe is 5 into 10 to the power minus 3 radians. If it is assumed that the electron source brightness is, which is B, is equal to 10 to the power 10 per ampere squared per sterradians, and the aberrations of the probe forming lens are neglected, then how many electrons pass through the probe per second? So we have a standard relationship for the probe current. So the current I through the probe is given by this formula. I is equal to B into pi d square by 4 into pi alpha square, where B is the brightness and d is the probe diameter and alpha is the semi aperture angle. So we can simply substitute these values. You can, if you want, you can write B's brightness d the probe diameter and alpha the convergence angle. So a simple substitution So what we have done is we have simply substituted all these parameters B, D and alpha, and then you get the answer something like 6.2 into 10 to the power minus 11 amperes. So the number of electrons per second is equal to I divided by charge of electron. So, we have the I value, that is 6.2 into 10 to the power minus 11 ampere divided by charge of the electron, which is 1.6 into 10 to the power minus 19, which is charge of an electron, which gives roughly 3.9 into 10 to the power 8 electrons per second. So, it is a very simple problem, but which involves simple substitution to bring the involving the concept of brightness, probe diameter and semi aperture angle. So, you see the number of electrons per second passing through the probe is given to be 3.9 into 10 to the power 8 electrons per second. So, the next problem So, the next problem is very interesting problem. Show by simple ray diagram sketches why spherical and chromatic aberrations are critical problems in high resolution electron microscopes, but not so serious in optical microscopes. What can be done to minimize these aberrations? Why is chromatic aberration more significant for light materials, that is low Z, that is low atomic number, than the heavy ones, that means with high atomic number? If you recall our lectures about this aberrations, in fact we have done elaborately discussed these aspects, and then we have also derived quite a bit of expression, mathematical expression, in order to quantify these aberration, whether it is a spherical aberration coefficient or chromatic aberration coefficients. We have 2-3 derivations we have done. So, if you go through that lectures, then it is very straightforward to solve this. So, the first part of this question, show the chromatic aberrations and spherical aberration by simple ray diagram. This is how it is written. This is a specimen, this is a lens, and this is an image plane, and this is how your aberration disk we talked about in the lecture in detail, and this is the the delta R due to spherical aberration. Of course, with appropriate magnification it will be there. And similarly, you have a chromatic aberration. The aberration disk is because of this kind of nature. So, you have this problem. We can write So, the second part of the question is, of course, it is a subset of the first question. These aberrations are not so serious in optical microscopes because in optical microscopes aberration free lenses can be produced, so that the resolution is limited only by the diffraction at the aperture, which has got the relation. I will write the relation. So, the resolution is limited by the diffraction at the aperture, which has got the relation, that is the resolution is affected only by this aberration disk diameter, which is because of the small d is for diffraction aperture, resolution is affected by the diffraction aperture. That means aberration due to diffraction is expressed by this formula, that is 0.61 lambda by alpha. But in electron microscopes, So, it is very interesting to look at this problem again. So, we asked why these aberrations are minimal or not serious in optical, because we are able to use the aberration free lenses, but the disk of least confusion, that is what we call it as delta R. If you recall the lectures, it is called disk of least confusion. So, that is only affected by the diffraction aperture, but in the electron microscopes spherical aberration cannot be totally corrected, very important. Spherical aberration cannot be totally corrected. So, the resolution limit therefore depends upon the semi aperture angle alpha. It can take two forms, it can be smaller or bigger. If it is smaller, then the delta R minimum is equal to delta R d, something like this. But if the semi aperture angle alpha is larger, then the disk of least confusion delta R minimum is equal to delta R spherical aberration. That means aberration disk due to spherical aberration, which is equal to Cs times alpha cube. So, Cs is the spherical aberration constant, alpha is the semi aperture angle. Or you can see that it is a compromise between these two extremes, that is optimum alpha. So, for the optimum aperture alpha, delta R d is equal to delta R s, like this. Then alpha opt you can write is equal to lambda to the power 1 by 4 Cs to the power minus 1 by 4. That means lambda to the power 1 by 4 divided by Cs to the power 1 by 4. And then if you write delta R minimum, which is equal to 0.61 lambda to the power 3 by 4 into Cs to the power 1 by 4. So, this is the resolution limit with the spherical aberration in place in electron microscope. So, this is the biggest difference between the light optical system and electron optical system. And then look at the final question, how to minimize this. So, to answer the later part of the question, to minimize the spherical aberration, a small aperture angle alpha must be used. And for the chromatic aberration, which depends upon the energy spread of the electrons, that is delta R chromatic is equal to Cc, this is chromatic aberration constant, times the semi aperture angle into the energy spread delta E by E. It can be minimized by avoiding fluctuation in the accelerating voltage or by increasing the voltage. So, if you increase the voltage, then this can be minimized, the energy spread can be minimized. The light elements, that is low atomic number elements, have stronger energy exchange with electrons relative to elastic scattering mechanisms than do heavy elements. That is, energy loss delta E will be larger and will lead to an increase in the delta RC. So, this is the answer for the last part of the question. So, the next problem will be, what we can do is, so the next problem is similar to what we have done, but it's a kind of exercise to relate this aberrations with the acceleration voltages. So, what is given is the expression which we have used in the previous problem for semi aperture angle, that is optimum angle, and the delta R minimum, that is disk of least confusion, and then we create a table like this for varying the voltage, namely 100, kilovolt, 500, 1000 with the obviously with the acceleration voltage changes, the lambda also changes, and you have the two options here for the alpha opt with the spherical aberration coefficient with two values Cs is equal to 1 mm, also for Cs is equal to 3 mm. Similarly, for the the delta R minimum, you have Cs equal to 1 mm and Cs equal to 3 mm. We can calculate and try to fill this table, that is the question. So, it is straightforward, you can do that, and finally and plot the data graphically. So, we can do that. So, I hope you can do it very easily with a simple substitution of each. So, you can complete the table simply substituting these values, and now we can also try to plot this, a simple sketch. So what we have done is, we have kind of plotted the optimum objective angle and ultimate resolution as a function of accelerating voltage. So you can see that very nicely, with the different spherical aberration constant, how this optimum angle and the ultimate resolution varies as a function of accelerating voltage. So you can see that with the increase in accelerating voltage, these things try to reduce. At least the resolution is increasing, and then delta R becoming minimal. And similarly, you will see that how alpha is also changing with the accelerating voltage. So with that, we will stop for this class, and then we will continue in the tutorials in the next class, where we will also try to solve some of the few more numerical problems, and then we will move on to some of the concept questions. Thank you.